right, so we're talking about data. I like to say that statistics is all about answering questions. It will feel like a bunch of numbers. It'll feel like a bunch of equations, a bunch of stuff that it's just going to feel overwhelming. I'm sorry, it's part of the process. But it can be pretty powerful, and you got to keep in mind that you're trying to answer something. I think that helps me a lot when I'm trying to think about it. It's trying to think about everything in context. The text says that the central questions of statistics are: how can data be best collected? How should data be analyzed? And what can be inferred from data? Again, all of these questions kind of circle around answering a question. Just a bit of a deviation from the natural resources or the ag stats thing is that I am a little bit of a baseball fan. I don't really memorize things. So I'm not like my wife can come up with, she'll just rattle off the whatever and knows everything. And I for some reason have this thing where I can't memorize things. I think I guess I can, but I've lost the will to memorize things. Maybe that's more like it. So I just kind of like sitting there watching the game and soaking it in. And I really like a live game, but I'll watch a lot of TV. I'll watch a lot of them on TV. In my other classes, you want me grading something of yours when my team is winning. Just so you know, if my team, and I also bad news for you, I'm a Royals fan. Yeah. So maybe don't take classes. Maybe, we were good once, and then again, 25 years later, another 25 years. It's okay. So anyway, I just like watching the game. And one of the things that I wondered going into the 2020 season, whenever they started finally playing, was how the reduced 60-game season was going to affect the stats of the players going forward. So normally there's 162 games. And so 102 games fewer, that might have some impact on the player stats from that year. So, why would that be important? Well, the players, obviously, it's a point of pride, if nothing else. But, it's also factored into the salary bargaining process and, a lot of other things. So it's important to understand the statistics of it. And you're thinking 60 games, 162, what difference does it make? What difference? Well, have you ever heard of the Sports Illustrated cover jinx? The idea is that if you're featured on the cover, that you're going to be jinxed and your performance will suffer. Any of you guys believe in that? Yeah? Yeah? It's the same word okay. Oh, yeah. I bet so. Well, so what's actually happening, so now again, I'm a baseball fan, so I can feel, I understand the idea of jinxes and curses. So putting that aside, so, clearly the Red Sox were cursed, and that had to be real. That's baseball fan Jason, stepping back into the professor role here, I have to tell you that, this is what we have is a phenomenon called regression to the mean. So typically your athletes are on the SI cover for an exceptional performance. They've done something really, really good to be on the cover, right? They're not, and the same for Madden. They had to be the hottest quarterback of the year. What's happening, is that the athlete probably has this latent or a true statistic, so maybe a batting average, that it's not to say that they can't get better or worse through coaching and practice and all those things, but it's that they have an inherent or a batting average that is theirs. Does that make sense? So what you're observing whenever they get to the cover is a temporary bump above their norm. So it's not so much that And what they're doing is they're reverting back to their mean. So reversion to the mean, or regression to the mean. Okay, so that's where I'm headed with this, is the idea behind that. So maybe the 60-game season reduces the amount of observations we have for, and this is getting to be an old story, so I'm going to have to come up with a new example for too long, unfortunately. Maybe it reduces the number of observations we have on players, and we are not able to see, maybe we'll see an uncharacteristically low or high amount of hits or whatever. So they will play uncharacteristically well or good or bad. And because we're going to only observe 60, we don't get to see what we would normally see in 162. Yeah. So in the stats software R, you guys don't have to worry about it. Don't worry about it. I'm the one playing with it. There's there's an access to the Lawman database where I can look up that data, and eventually we'll get to the difference piece. Right now, we'll just start working our way through some of the data on what it is and what we're looking at, kind of as an example in this context. So if we were wanting to look at batting averages, we need to know the number of times a batter gets on base and how many times the batter is at bat across the season. A count of times on base, okay, that's numerical, right? We have we're counting something. Specifically, it's discrete, meaning that it only takes on whole numbers or integer values, and count data, meaning that it takes on a count of observations. So, I mean, you can have a discrete negative number, but you can't have a negative count data. We need to count the times at bat. Again, that's numerical, and again, count data. So both of these are discrete. They only take on integer values. And just as an illustration, I did not draw this. This is Allison Horst. She drew this, and I just think it's too awesome not to show you. A continuous number is like measured data. So you can have an infinite number of values within this possible range. And so, this chick is 3.1 inches tall and weighs 34.16 grams. If you had the precision to measure more precisely than 3.1 inches, you could, right? I mean, you could measure this thing to the level you have precision to measure it. And then you can also have discrete, though. So we have observations that can only exist at limited values. Usually it counts. So this purple thing has 8 legs and 4 spots. Counts. Makes sense, right? What about categorical data? In our question at hand, it doesn't really matter, but we could also have a variable that was maybe indicating if the player was early, mid, or late career, and that would be what we call ordinal. We could also have a variable that would indicate the number of the season, 2018, 2019, 2020. Now, this can be confusing, but in this case, we can treat those numbers differently, because we're not actually. It's not like years can be tricky, and what we're going to use years for is to group into groups. So the 2019 season, the 2020 season. If you were doing something where you were measuring growth per year, okay, well that might warrant a different treatment. So basically, what we're treating years as categorical. You could treat them differently. You just need this. I know this is coming back to the idea. You got to have an idea of what your data is and what you're doing with it, so that it makes sense. If we thought race mattered, or if we had access to that data, that would obviously be categorical. But that would just be nominal, in that the categories aren't ordered. We would just say that someone is what they're categorized as, but there wouldn't be an ordered hierarchy among the categories, like there would be between early, mid, and late, or 18, 19, 20 seasons if we were using it differently. Yeah, makes sense? Cool. Okay, just as an illustration here, though, we have nominal. So those are the unordered descriptions. I'm a turtle, I'm a snail, I'm a butterfly. There's no ordering there. But we could have ordinal, so ordered descriptions. I'm happy. Well, okay, that's less good than being okay, which is definitely less good than being awesome. But we can also have, and I didn't say this earlier, we can also have binary, where we say, I'm extinct. That is or isn't, right? A little bit dead is you either are or aren't. And often, just as an aside, we will represent binary data as ones and zeros. So ones is taking on the characteristics. So if we were looking at a data set of animals and a dinosaur was there, it would be a 1 for extinct. If we were looking at sharks, well, shark's not extinct, so that would be a 0. Make sense? Cool. Okay, what about populations and samples? Well, with baseball, this one gets tricky. And let's think about something else for a bit so that we can come back to baseball and so that we can talk about populations and samples. First thing is that we can calculate a population parameter. So we were calculating mean, which we'll talk about what the mean calculation is, but for height of all chicks. Okay, well, that would be quite the task, wouldn't it, to measure all of the baby chickens in the world? Or we could estimate a sample statistic. So again, maybe if we wanted to look at all the chicks in the world, we could grab some samples in some ways and only measure some of the chicks in the world. And my example here, so you guys have you heard of the woolly worm, the woolly worms, the old wives' tale about them? No. Okay, so what this is that it, depending on the proportion of black to brown on the woolly worm, tells you how the winter is going to be. A more black woolly worm indicates a harsher winter than a more brown woolly worm. This is just I'm from Missouri. Maybe we made this up. Anyway, so if you wanted to do that, are you going to measure all of the woolly worms? No. I mean, first of all, I don't know where you would find them all, but you're definitely not measuring them. You can't possibly measure all of them. You couldn't even do it with a grad student. Grad students, you can do anything to them, and you can't do it. So you're going to have to take a sample somehow, so that you can systematically select some of the woolly worms to measure. Now, why does this get complicated for baseball? It gets complicated because we can observe every game at bat. So the fact that I'm looking at a database of every MLB player since 1871's batting stats, and it's only 107,000 observations, these are trivial calculations. It would have been that long ago, it would have been a problem within y'all's lifetimes, believe it or not. It would have been, but it wasn't by the time you were in elementary school. So but it's a pretty trivial task. We can measure anything we wanted to. Now, maybe we are only observing the population of at-bats for a given player, or we can only observe a certain amount. In any case, this is something for baseball we'll have to keep an eye on. We're not, for right now, this chapter doesn't so much matter. Now, I just kind of spoke broadly about samples. I didn't really tell you how the samples are taken. There are actually several ways to take samples. We can do what are called convenience samples, which would be, say, I just watch Royals games and I compile the observations based off the fact that I watched the Royals games. Does this sound like a good idea? No, this is bad. If we were only going to talk about Royals players, then okay, maybe. But it's definitely not a way to talk about all of MLB. Okay, so what about another way? I could compile data on a random selection of players that were active in 2019 and 2020. Just at random, grab some out of the database and look at them. Okay, well, that's actually something that could work. Now, are there any other kinds of samples where we're talking about sampling? Yes, we have stratified sampling. So first we would divide the population into stratum and then sample the subgroups. And the stratum can be a lot of things. But it's a characteristic of the observed. So in this case, we could divide MLB into 30 teams or whatever and sample the teams. Or we could divide players up by salary, by year of entry into, by a characteristic of the players. Okay. We could do a cluster sample, in which case we would divide the population, so all the players, into subgroups, and then sample the subgroups. So, but instead of we're gonna divide them up again into 30 random groups this time, and then we're going to choose which of those groups to measure, and we will measure every individual within that sampled group. Does that make sense? It doesn't make it. I've never. I don't know of a reason why you would do this, but it is a thing somebody has thought of to do.
So whenever you would divide a cluster, would it just be a random selection, or would you pick a characteristic like you would with strap?
My understanding of it is that it's at random, which maybe I'm probably overlooking a reason why that was thought of. Somebody thought of that for a reason and was like, oh, this is a way to overcome a problem, probably. But I just don't know what it would be. You can also have a multi-stage sample, which is like a cluster, but instead of keeping all of the individuals within the sample groups, we sample again. So we divide MLB into 30 groups and then sample within the subgroups. So if there are 20 individuals in each of these 30 groups, you don't measure all 20. You only measure maybe 10 at random. Make sense? Okay. Okay. It's back to the simple random sample, because that's really is the better way of doing things if you're wanting to make statements about the whole population. Now, it is a good thing that we don't rely on these players to compile their own data. If there were, if somehow you were surveying the players for their own batting averages, well, first of all, they probably lie. But leaving aside the lying piece, just for some reason, this is a silly thing to throw out. Let's just say that for some reason, players with families never turn in their cards. I don't know why. I'm making this up. Well, so if that were to happen, then that would mean that only players without families would return their cards. And that would be a problem. Then we would have what's known as a non-response bias. Now, again, this is a silly, stupid example. I'm not trying to pick on an actual characteristic where that might actually lead to be. Now, what we could do is maybe maybe it's not that none of the players with families respond. It's that few of the players with families respond. Well, if that were the case, then we can do what's known as again, a stratified sample, like we were just doing. But then we're reweighting, we're giving more weight to the observations of players with families to compensate for the fact that some of their fellow players don't respond. Now there's a whole bunch of stuff that goes into that bullet that we're not covering. I'm just letting you know that that's out there. So back to our world of ag and natural resources, the NASS, National Agricultural Statistics Service, is a part of the USDA. They compile data on farm operations, and that's their sampling techniques, because not all farmers respond to the well, they don't actually respond to all of the census either, but they don't respond to the surveys, and they stratify their sample so that if they get a sample of, say the large farmers respond less often than small farmers for some reason, well, they stratify it so that they can compensate for that and weight their statistics so they know how many acres are planted in corn or whatever. And they don't have a bias, a non-response bias. So that's just something to be aware of, something you got to think about whenever you're making these. Now, again, so what if there's another piece of this. You have observational studies versus experiments. Looking at this 2020 season and the seasons leading up to it, I'm using data that already exists in the world as it already stands. So that's an observational study. And that's a space where I'm comfortable. I'm an ag economist by training, and they don't let me assign like your wealth. Like I can't just grab a random sample of people and conduct experiments on you. They won't let me do it. I mean, just makes science hard, guys. No, they won't let me do that. But now, because it's unethical, by the way. But anyway, but what if I wanted to study like the effect of a drug or something like that? Well, then I really, really need a controlled environment. So if I wanted to know what the effect of some drug is, I would need to have, I would need to design an experiment. And we don't need to go into the details on that. That's another course entirely. Again, I know I keep throwing these things out there. It's like, well, this one bullet here, that's an entire course if you were going to something else. But so we're not going to go deep into it. We would need to do something so that we would need to design it in a way that we don't get thwarted by what we call unobserved data points. So if you were, I don't know, if certain people could tolerate a drug better than other groups of people, but you don't really know why, maybe you would want to know why as you were determining this example or this experiment. So should have come up with an example for that. But anyway, that's that. So here are 5 random rows of batters in 2019. In the terminology of the textbook, they would call that a data matrix. All of it. I'm going to end up calling it a data set. So that's why I put it in parentheses, because I want you to know if I'm talking about a data set. That's what I'm talking about. I'm too old to train for new tricks. So what we have in each of the rows is an observation. Now you can see enough of it to know that it says observation. That's going to be a problem in a little bit. Player ID, we can treat it as a variable. Basically, you get the idea. Each column is a variable. Okay, what kind of sample is this? I took it at random. It's a simple random sample, just that easy. I told the software I want 5 random observations. That's what it gave me. We're going to do some calculations as we're calculating these things, and we got to remember our order of operations. The parentheses especially throw people off. So remember that remember the PEMDAS. Please excuse my dear Aunt Sally. I don't know what they teach y'all now, but parentheses, exponents. Remember that a radical, so a square root or cube root or whatever, is an exponent. It's just that it's represented differently. So multiplication, division, addition, subtraction. What might be useful to know? Maybe we want to know, again, at-bats. How many at-bats are typical? So I grabbed those 5, and I mean, this is clearly, these players are just alike, aren't they? I mean, they're, oh boy. Okay, so we have 89, 324, 0, 136, and 20 at-bats. Well, anyway, this is our sample, so let's do our calculations on it. Sometimes you get your sample and you don't like it, but it is what it is. Okay, we might need the mean. To find the mean, you simply add together all of the values that you have there, divide by the number, and that's the mean. Okay? And that's a measure of central tendency. So that gives you an idea of what's I'm not going to say normal, what's typical for the group. 113.8. Okay. Well, with a 0 and a 324, that's not great. Maybe we ought to look at a median. So to find a median, what you do is you put them in order. So now we're in 0, 20, 89, 136, and 324. You just put them in order like that. And the median is 89 because it's in the middle. Just that easy. Now, what if, like I said, you're going to line those values up in ascending order, and the middle is 89. What if there was no middle? What if there was another number? So I'm just going to throw on 325. I made it up. It's not part of the sample. Let's just throw that on there. And what you do then is you find the 2 middle values and average them. So 89 plus 136 divided by 2. That's now your median is 112.5. Again, it's still a measure of central tendency. We're still measuring what's typical of the group. So that's median. Sometimes median, I usually like to see median and mean both. It gives you an idea of the distribution of the observations and how normal they are, which we'll talk about a little bit. Anyway, but interquartile range, IQR. Okay, so we still have our sample of at-bats. The IQR is the range between the 25th percentile and the 75th percentile. And yes, with 5 observations, this is silly. But it's still the same. It's the same calculation with 5 as it is with 100,000. So again, we want to order the observations: 0, 20, 89, 136, 324. Then we want to use this formula. I is equal to K over 100 times N plus 1. And what we're doing here is we're finding the observation that we want to look for. So, and by the way, this works for median too. So if you get to a weird, and you don't think of another way to find the median, this works. So let's look for the 75th percentile first. I is equal to 75 over 100 times 5 plus 1. And that equals 4.5. Okay, so there is no 4.5 or 4.5. You can't even say it. That observation doesn't exist. It's not a whole number. So you round down, find the 4th observation, and round up, find the 5th observation, and average them. So 136 plus 324 divided by 2. This is one of the things that I think the book could be a little more plain spoken with, just in case you're reading along and you miss it. It's pretty, you could use a little more discussion on it. Okay, so that's how you find the 75th. Now, I want to find the 25th percentile. That is 25 divided by 100 times 5 plus 1. Again, 1.5. Do the same drill. 0 plus 20 divided by 2 is 10. So that's our bottom 25th percentile. And our I don't think I have it on here. So our IQR is equal to 230 minus 10 220. So that's what our interquartile range is. Okay. Did you get that? Okay, these guys have way different batting averages. Would it be useful to know how different they are? I mean, not even like, we're used to looking at central tendency, but maybe we ought to be looking at dispersion. We ought to be looking at how different these things are. We can look at the variance. There's the formula for the variance. And then I'm going to work through this in kind of the hard way so that you can see it done. So here's our at-bats again. Okay, so you can see the part you need to see. The numbers are there. That works. So we have 89 minus 113.8. 113.8 was the mean. So that's the X bar in this formula here. And that is equal to negative 24.8. 324 minus 113.8, 0 minus 113.8, 136 minus 113.8, 20 minus 113.8. Make sense? Okay. So then we take that and then we square it, square it, square it, and square it. Then we add together all of these values that have just been squared. That's what this is right here. And then once that's been added together, we divide the value we've got by n minus 1. 5 minus 1. for a variance of 16,760.2. What does that mean? Well, that's actually really hard to tell you because it's in a unit squared. So it's the number of at-bats from the normal deviation of this number of at-bats squared, which is really hard to interpret, right? What's easier to understand is standard deviation. Standard deviation, we take the square root of the variance that we just found, and that is equal to the standard deviation. And what that means is it's the measure of the average distance between the values of the data in the set and the mean. So how different they are. On average, a player will have 129.4612 more or less at-bats than the mean. That makes sense? This is, I took it out on the previous slide. This was just the code, and I should have took it out on this one. So it is much, much easier to do in software than by hand. You need to learn how to do it by hand, in my opinion, so that you know what's happening. And you don't have computers at for the exams and stuff. So on average, a player will have 129.4612 more or less at-bats than the mean. So I would say that there's a problem with the sample. So what would be a good thing to do? Get a bigger sample. Really strangely, you could just look at all of them and use a population instead of the sample. But again, we're still trying to work within the framework of this stuff here where we don't actually normally get to count them all. There's a mathematical fact, I don't know how else to say it, that as your sample size approaches infinity, so as your sample size gets bigger, you get closer and closer to the true measure. So again, remember I was talking about there was some latent characteristic of this player before he ends up on he or she ends up on the cover of Sports Illustrated. So there's some characteristic that they have that is they have a really good batting average, or they have but as we observe more and more and more, we're going to see what the true value is. So if we were to measure heights of every student at Tech, well, again, it's what, 12,000 of y'all? That's doable, but it takes some time and it'd be kind of costly. So if we took a sample of 5 of you, that's not going to be a great sample. If we took a sample of 1,000 of you, it's probably going to be a pretty close sample as long as we were not, if we weren't biased in how we did it. If you did it outside of the gym, you're probably going to end up with a little different sample than you would end up if you did it outside of, I don't know, someplace where shorter people hang out. The gym. Yeah. Someplace else. I'm somebody who hits my head frequently. Okay, so what I'm saying is that assuming it's a random sample, and the bigger a sample you get, the closer the sample gets to infinity, the better we're going to be able to estimate what that true population parameter is, because we're calculating a sample statistic. So our sample is the sample mean. So if I measure all y'all's heights and I say that's my sample, well, that's a convenience sample. We're not doing great right now as far as science goes, especially if we're trying to describe the heights of campus, of the entire student body. But there's only like 15 of you in the room, 10 of you in the room, something like that. It's not a great number either. If we grab more and more and more of you, we would get closer and closer and closer. Our sample statistic of your all's height would approach the true population parameter of the university student body height, average height. Make sense? Okay. Now, we can, to look at this, maybe we'll want to draw, or we could visually assess this with a graph, but that's really not that. I look at data all the time, and I don't really know what to tell you about that. Maybe we ought to look at the mean, median, standard deviation, and the interquartile range. Okay, so what we can do is we can plot a, losing my mind, whisker plot, or a box plot, and we have, let me get my laser. We have, and this is a kind of a tough one to see because you see how close it is to zero. It's bunched up. So the 50th percentile here is this heavy bar. That's our median. So median is 7. Our bottom 20, our 25th percentile is probably 0. It's right there close to 0. Our 75th percentile is up here at probably about 100, 144 would be my guess, because the interquartile range is 144. So this line here, 75th percentile. The heavy line, 50th percentile. The lighter line that would, if you were looking at normal data, this would go on and it would look more like 2 rectangles stacked on top of each other. It's not normal. It's okay. 25th percentile. Now these whiskers, this line right here, they extend plus or minus. So above the 75th percentile, it's plus 1.5 times the interquartile range. So 1.5 times 144. That's how far this extends. And then below, it's Q1, so the first quarter or the first quartile, minus 1.5 times the interquartile range, or until you reach the last observation. In this case, I mean, you don't have negative at-bats, so 0 is where we're stopping there. That's why there's not a line going off into this space here. It's not a thing.
So is 1.5 a constant then?
Yes. Yep. Sure is. And I've seen other rules on this. This is what the text says. So now these red dots up here, believe it or not, these are all dots individually. These are not, it's not a line. They are what we call outliers. They lie beyond this value here at the end of the whisker. Basically, I would call them extreme values. They're unusual for the data set. That's an outlier. So these ones up, these observations up here. All right. Another way we can measure things is by counting the number of times we observe them. So if we have at-bats on the bottom side here, these are all whole numbers. So we can, some people that have 0 at-bats, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. You just count the number of times you observe them. This is what we would call unimodal. So the mode is the most frequently observed value in the data set. So it's another measure of central tendency. In this case, it happens to fall on the left edge, which happens. But we have one most frequently observed value here. And then they all kind of go off to the right here. This is what we would call very right skewed, meaning that it's kind of like it's been drug off to the right. Just that. what I keep referring to is something called normality. What that is there is a frequently observed pattern in the world where observations tend to fall. So again, if you want to talk about height of students on campus, I don't remember what the average male height is. It's like 5'10", 5'11", something like that. Anybody have an idea? It's all 5'11". That means if heights were normally distributed, then you would most often find males who were 5'11". If it was normally distributed, that's the mean. There's going to be most of the time that's what you're going to find. Slightly less frequently, you're going to find 5'10" or 6'1" or 6'0", 6 foot. I went 1 inch out, and you find a few fewer observations. 2 inches out from the mean there, a few fewer observations than what I just said. And you end up with something that looks a lot like this. So if this was 5'11" for the height, and this is the number of observations, and this is the height here. Well, 5'11" is going to be our highest, and you get down here, and you don't find a whole lot of people below 4 feet, but they exist. Down here, you don't find a whole lot of people over 7 feet, but they exist. You can go back in time, find some people, 13, 14 feet tall, and Goliath. Anyway, it's a characteristic. It's something that you tend to find, and if you don't find it, it's notable. It's something to note that, I measured this thing, and it turned out it was not normally distributed. It's not. Yeah. Now, let's see here. So we have another histogram, and this is what we would call a multimodal, or in this case, I would say bimodal, because there's two. They're not exactly the same. It doesn't have to be, but you notice how there's two peaks here. A lot of times, there's kind of a misconception that grades are normally distributed, and they're not. In my experience, grades are more multimodal, bimodal at least, where you have a lot of people getting D's and F's and a lot of people getting A's and B's, and hardly ever, usually don't have a peak in C's. It's been my experience. You can also have, if it's not normal, then there's a measure, and you don't have to worry about how to measure it, but there's, because this is represented as a number, but you don't have to worry about that. This is what we would say is left skewed. It's left skewed because here's our mean, and you see how that tail goes way out to the left a lot further than it goes to the right. So it looks like that left side's been kind of stretched. That's if you had watercolor and you were doing this instead of on a computer, and you just went ship, that's what it would look like. So that is skewness. I already showed you a right skew. That was the at-bat data. Okay, what about categorical data? Again, what we were talking, I made mention of maybe we could measure the seasons. Maybe we can measure if race mattered, we could measure that. But what we can do is we can measure what team they're on from our sample. And apparently, I managed to grab a whole bunch more San Francisco players, not a whole bunch more, but more San Francisco players than any other players. Kind of interesting for a random sample. And really interesting to me with the 43 Seattle. And they haven't been a team in that long. Anyway, yeah. So those are the number of players in our random sample that are in each team. So that's a frequency table. For categorical data. We could also do a bar plot where it's kind of like a histogram, only for categorical data, where we count the number of teams or observations per team. So that's one way. Now, another measure that's kind of useful is correlation. It's measured by this calculation here, and it's kind of gnarly, but it's not too bad. So if you wanted to measure this, you would, if you had all of these values here and of X and Y, I think that this was games played versus RBI. Yes. So, you would have all of one series of numbers here of X's and another series here as Y's. So I think these are games played and these are runs batted in, RBI. So you would have XI, 31 for this first one, minus X bar. The mean of that 1,000 observations is 45.877. Divide by the standard deviation of that value. So the observation, the ith observation minus the mean divided by the standard deviation times, you multiply that by the Y. So YI, so this is 11 minus 14.271. 14.271 is the mean of Y divided by the standard deviation of Y, 25.87975. Then you're going to add all of those together. So each ith observation. So we did 31 and 11. The next one will be 50 and 0. The next one will be 40 and 0. The next one's 79 and 22, so on. And then once you've got all those added together, you multiply that by 1 divided by the number of observations minus 1. So 1,000 minus 1. And we get this statistic R, which is a correlation coefficient. And that tells us how related they are. So if they move, or how the values, I say move together. So a correlation coefficient of 0.87 is pretty good. I mean, it's close to 1. It's pretty close to 1 there. And it's positive. So if we were to plot this on a scatter plot, so runs batted in vertically, games played horizontally, our R here is 0.87, and you see how that kind of goes off to the upper right. Now, this equation right here is for linear regression. You don't need to worry about that today. We'll get to that at the end, but at the end of the class. And what's happening is that we're plotting a line that fits most of these, basically by reducing the distance between, or to minimize the distance between each individual observation and this line. So we plot this line, and we can kind of get an idea of how many runs batted in we should expect out of a certain number of games played, if that's if that's a valid thing, I'm saying it's not, but because we know the data. This is a positive relationship with a strong correlation coefficient, though. And that really does, I mean, it exhibits strong correlation. Now, you're not going to see this in a homework or on the exam, but you do need to be careful whenever you see a cluster like this at 0. That indicates a possible problem with how you're going to interpret the data. Not so much important right now, though. Okay, so this is a different one. This is hits versus RBI, and this one makes more sense. Has a higher R value, so it's even stronger R, meaning it's more correlated. It's still positive, so it still moves off towards the upper right. Now, and again, something you're probably not going to see on an exam or homework is this kind of fan shape is a bit of a problem. But again, that's for much later in the class. Right now, all you need to understand is that this R, this correlation coefficient, is quite high, and these are definitely correlated, which makes sense. I mean, you really ought to. You have to hit the ball. You have to have a hit before you can have an RBI, right? So this is kind of a silly example, but in any case, though, it shows the plot. So this is what a positive, highly correlated positive, highly positively correlated would look like. It could go off at the if you had a whole bunch of points, you could have a correlation that went that direction. That would be negative. So ignoring the black points on the graph and only looking at the red, if it was like that, that would be a negative correlation. It's downward sloping. Yep. Okay. So then we have contingency tables, and they are a way that we can summarize categorical data. We have, honestly, I don't actually know what the context of this is. I just grabbed the table off of an image search. But it looks like you got a survey of male and female, and maybe you're asking about the preferences between dog and cat. I hope that's what it is. That's what I'm saying it is. Maybe males have a preference for dogs and cats, and females have a preference for dogs and cats. So we can summarize this: male people, female people. So what % of males prefer cats over dogs? That'd be a useful thing to know. So you have a male prefer cats over dogs. So 10 divided by 52 times 100, 19.23%. Again, these are, since I don't actually know the context of the table, completely made up. Okay. What % of the respondents overall prefer dogs over cats? Okay, we got dogs as our total. See, what you're doing is you're adding these across here, or down and across. Got our total is 51. Our total of all observations is 100. It's 51 divided by 100 times 100 is 51%. Okay, what % of those preferring cats are female? Okay, so 39 are female who prefer cats, and 49 of the whole sample prefer cats. So 39 divided by 49 times 100. 79.59%. So what we're doing here, and it's just easier to tell you in examples, is you're looking for a statement that's telling you the out of, and then the what you're measuring within. So what percent of males? So this statement here is telling me that I'm looking at a total of males. And what I'm measuring within that is those who prefer cats. So cat. Does that make sense? Just, okay. That's actually all I have for the day.